Okay, all right. We'll begin then. How are you guys doing? It's week 4, so halfway through the quarter already. And so last week we kind of concluded our covering of neural networks, and now and you guys are working on that for homework. And so now we're going to look at other some machine learning algorithms, and what we'll look at will be some classification algorithms. And so we'll look at a Bayes classifier first, and then we'll also look at the naive Bayes classifier. Okay, so these are algorithms that allow us to predict a category. All right, so a lot of the other stuff we've been looking at were used for predicting a numeric variable. We've been using, mean squared error. You predict, some kind of number like race time, winning race time against, the input variable x. We did have a little bit of classification with the neural network for the digits classification, so we can see how we can configure a neural network to make categorical predictions, a classifier. And we'll look at a few other, methods for us to make categorical predictions. So this is the notation that our textbook, a first course in machine learning, uses, and so a lot of the stuff we're looking at comes from chapter 5. So we have these observations, they call these training objects, so observations in our training data, and we have n of them, and they are represented with these vectors x. Okay, so those are the vector x. There are d values, so you can imagine a matrix with d columns, and you have these different variables. So, for example, in your homework, you're looking at the IRIS data set, and you have, I think, 120 observations in your training data, and you have 4 columns. And so each observation would be a vector of those 4 values, the petal length, petal width, sepal width. And each of those observations is associated with some kind of label, okay? And in the IRIS data set, your labels are setosa, virginica, versicolor. And here we would label these class 1, maybe setosa, class 2, virginica, class 3, versicolor. Is that the order that they're in? I don't know. Maybe they're in a different order, okay? And our goal is, if we get a new observation, and it says, here's a new observation, in your test case, it says, the sepal length is whatever, 4.6, and the petal length is this, and whatever, can we predict, accurately what kind of class, which class it belongs to? And again, what's very important to remember is that these are categories. So even if our categories look like numbers, like category 1, category 2, category 3, they are not numbers. It is not correct to say category 3 is higher than category 2, which is higher than category 1, or something like that, right? You don't look at your phone number and say, I have more phone number than you. Okay, you don't compare your phone numbers and say, my phone number starts with an 8, your phone number starts with a 3, my phone number is higher than yours. We don't make numeric comparisons like that. And similarly with these class labels, even if they're coded as integers, we don't make numeric comparisons. We are what we're going to look at is the Bayes classifier. The Bayes classifier is a probabilistic classifier because it tells us what probability it believes the observation, is in this particular class. So it'll say, I think it belongs to class A with probability 19%. I think it belongs to class B with probability 80%, or something like that, okay? Other probabilistic classifiers are things like logistic regression. It gives you a number between 0 and 1, okay? There are other classification models that do not do probabilities. So for example, a support vector machine, which we'll take a look at later, will kind of say this is class A and this is class B, but there's no probability associated. Okay, k-nearest neighbors also gives you a class label. Technically, I guess you can do a probabilistic thing with k-nearest neighbors, but generally it's treated as kind of a hard rule. This is the Bayes classifier. Don't mix it up with Bayesian statistics. So Bayes, the word Bayes gets thrown around a lot. And so even though this is the Bayes classifier and it uses Bayes' rule, it is not considered Bayesian statistics. I will be teaching 102C in the fall. I don't know if any of you are taking 102C with me in the fall at 8 a.m. But if you are, I'll cover some Bayesian statistics there. And it's, something different. And we have our parameters themselves are random variables there. Okay, but anyway, for the Bayes classifier, we use Bayes' rule. And this is Bayes' rule, right? The probability of A given B, I think this is from Stats 100A or 170S or something, or Math 170S something. Okay, A given B, probability of A given B is the probability of B given A times the probability of A divided by the probability of B, right? This numerator, probability of B given A times the probability of A, is equal to the probability of B and A or B intersection A. And then this denominator can be decomposed into basically, the probability of B intersection A for, this part of A, and then, all of the different components of A, okay? All of the different categories that A can take across. Or we can basically say the denominator is equal to the numerator if you sum it across all of the different possible categories of A, or values of A. So we're going to apply Bayes' rule to the classifier. And so this is what we want. What we want is the probability that our new observation belongs to class C. And it's going to be based on the values in our X. Okay, the new observation has X values, right? So, it says petal length is this, and petal width is this, sepal length is this, sepal length is that, or sepal width is that. That's our X values. And given those values, we want to figure out what is the probability. The label is setosa. Okay. We also say given all of our training values X and our training labels T. And so we're going to use Bayes probability. And so you can kind of think of this as, what we're looking for. So I'm going to go back a slide. We're looking for A given B. So we're going to call this part the A, the probability that we're in class C. That's going to be our A part. Given B, the given part, the B part is going to be X new. And so if you use Bayes' rule, we're going to flip these around. Oh, okay. Just side note, the answer that we're looking for, this thing that we're looking for, is a probability. So just general probability rules, it's going to be a number between 0 and 1. If ever in your calculations you get something that's outside of this range, you did something wrong. Okay, and then the sum across all of the different possible values of C have to add up to 1, right? So if we have an observation and there's only 3 possible labels, setosa, virginica, versicolor, all 3 of those probabilities have to add up to 1 because it has to be one of those 3 things. Okay, so if you think about Bayes' rule, probability of A given B is B given A times probability of A times the probability of B, and we apply it to this, and we say the probability that this new observation belongs to class C corresponds to A, and the X new corresponds to B. Okay, the given X and T, given our data, given our training data, is going to remain part of the given part everywhere. But here we say, okay, the probability of X new given that our observation belongs to class C times the probability that our observation belongs to class C, that's our probability A, divided by the probability of getting these X values. Okay, we label these things in Bayes' in Bayes' rule. We call this part the posterior. This is the probability that we want to find. We want to find what's the probability our observation, our new observation belongs to class C. This part right here, this is our likelihood. It's the probability of getting these values x new if we assumed it was in a particular class, right? What is the probability of getting a petal length of 5.1 if it was Setosa? What's the probability of getting petal length 5.1 if it was Virginica? What is the probability of getting petal length 5.1 if it was versicolor? So that's what this part is, okay? The prior is just what is the probability that it belongs to a particular class? So before you even look at the data, prior to looking at the data, that's where the word comes from, if you knew your population was, I don't know, 90% yes and 10% no, whatever question it is, okay? Before you even look at the data, if you just picked one at random, what's the probability it's going to be yes? You're going to say, oh, before I even look at the data, I'm going to just guess it's 90% yes, okay? Then you look at the data and maybe based on what you see in your data, you're going to say, okay, this is, we're getting something different, okay? But, that's the prior probability, okay? Before the probability that an observation belongs to class C before you know anything else about it, okay? And then in the bottom we have what we call the marginal probability, and this is what is the probability of getting these values in x new, petal length 5.1, regardless of class label, whether it was Setosa, Virginica, or versicolor, whatever it is. So what we're going to do is we're going to expand this denominator to simplify our calculations. And it looks complicated, but basically we're going to just say this thing is equivalent to the numerator if you add it up across all of the possible things that C can be. So we're going to say the denominator is equal to the sum of the numerator across all possible classes. So that's going to be equal to the sum from C prime equal to 1 to big C, meaning we're going to do it for class 1, class 2, class 3, however many classes we have, and we're going to calculate the numerator for all of these things. And that's going to, basically, it's just a scaling constant, okay? Because when you calculate the numerator, you might get 0.2, 0.3, 0.01, okay? 0.2, 0.3, 0.01. And so when you add those up, those add up to 0.51. Okay, that doesn't work. They need to add up to 100%. They need to add up to 1. So you're going to do 0.2 divided by 0.51, 0.3 divided by 0.51, 0.01 divided by 0.51, and then you'll get numbers that kind of add up to 100%. Okay, so we're going to look at a silly example, just a very simple example to kind of illustrate how the Bayes classifier will work. So we're going to imagine you go online and you buy some marbles, okay, and they come in little bags, and we have the marbles are either red or blue in the bag. Yeah, I guess we're going to order 25 bags, 25 pouches of marbles, and I don't know, you look at the serial numbers or whatever, and you can tell that these marbles, the bags are coming, the pouches are coming from 3 different factories, okay? And maybe these factories are operating a little bit differently. We have at factory A, so we have 25 bags total, 24 are labeled, that's going to be our training data, and we have 1 left over for our test case, okay? Out of the 24 bags, half of them, 12, come from factory A, 6 come from factory B, and 6 come from factory C. So that's going to serve as our training data. And we're going to assume our bags are filled based on like a binomial or Bernoulli process. Basically, I don't know, randomly it's going to be red or blue, and the probability that it's red or the probability it's blue is going to be constant throughout the thing. Okay, so 25 bags, 24 will be our training data. We have 1 test case here. And so, we open up our training data and we count, okay, how many marbles are red, how many marbles are blue, And out of you look at all 12 pouches from factory A, overall, 60% are red, 40% are blue. Okay. When you go to factory B, the 6 pouches that came from factory B, you get exactly 50% red, 50% blue. And when you look at factory C, you get 40% red, 60% blue. Okay. But again, you have a little bit of variation. It's not every single bag is exactly 60% red and 40% blue, right? It's random. So this bag was 60% red, this bag was 65% red, this bag was 50% red, and this bag was 55% red, or something like that, right? You have some variation, but overall, the probability for factory A is 60%. Overall, the probability for factory B is 50%, so on and so forth. Okay, does that kind of make sense? The setup of our things, and so based on what we see in our training data, we will get maximum likelihood estimates for the proportion for each factory. So just based on this, because in our data, 60% of the values, or 60% of the marbles coming from factory A were red, we are going to assume overall factory A has a filling proportion of 60% red. That's going to be our maximum likelihood estimate. Okay, and we're going to assume factory B is 50% red, and we're going to assume factory C is 40% red. Okay, so what we do now is we take our test case, we open up the bag, and we dump them out, and we get 20 marbles total. 10 are red, 10 are blue, right? So in our test case, our bag is 50% red. Okay, so we ask, could this bag come from could the bag we have, could it have come from factory A? Could it have come from factory B? Or could it have come from factory C? And the answer is technically all 3 of these factories could have produced a bag that was 50% red. Okay, what is the most likely factory? The factory that's most likely is going to be factory B, right? Because factory B overall is 50% red, and that's what our bag is. Our bag is also 50% red. So that kind of seems like it's the most likely case. But we say, well, could factory A have produced a bag where it's 50% red? And the answer is yes. We can just do the binomial probability to figure out our likelihood. We're going to say, okay, what is the likelihood that factory A produced this bag of 10 red and 10 blue marbles? And so we say, okay, well, we're going to do 20 choose 10. Factory A has a filling proportion of 0.6, so we're going to do 0.6 to the 10, 0.4 to the 10, and we get a likelihood of 0.117. Okay. What is the likelihood factory B produces this? So we have, same thing, but now factory B is 50% red, so we do 0.5 to the 10, 0.5 to the 10, and we get 0.176. What is the likelihood that factory C produced this bag? And so we're going to do, probability of red is 0.4, 0.4 to the 10, probability of blue is 0.6, 0.6 to 10. And because, this symmetric nature of it, it's also the likelihood that it came from factory C, or the likelihood of this data, okay, is, if it came from factory C is 0.117. Okay. All right, does that kind of make sense how we're getting these likelihood values? So we're saying if we assumed it came from factory A, what's the likelihood of getting 10 red, 10 blue? If it came from factory B, what's the likelihood of our getting? Okay, so this is great and all, right? But do we just stop here? And the answer is we don't stop here, because what we also need to take into account is that when we looked at all of the bags, it wasn't A, B, and C were equally likely, okay? Before we even opened up the bag, remember, half of our training data came from factory A, a quarter came from factory B, and a quarter came from factory C. So before I open the data, if you just had to guess which factory it came from, okay, then before you opened up the bag, you would have said, well, based on what I see in our training data, I would give it a 50% chance that it came from factory A, a 25% chance that it came from factory B, and a 25% chance it came from factory C. Okay, so that's going to be our prior probabilities. Okay, so before we even looked at the data inside, if I said, what is the probability that it came from one of these particular factories, we would just say, okay, in our training data, half the bags came from factory A, therefore, I think this bag is 50% probability A. In our training data, a quarter of our bags came from factory B. So prior to looking at the data, I'm going to assume it's 0.25. Okay, and so we want to combine this prior knowledge, or just kind of the knowing that factory A is kind of responsible for most, or half of the marble production. All right, we want to balance that with what we see in the data, right? So what we saw in our data, the likelihood was, according to this, factory B is the most likely. According to our prior probabilities, factory A is the most likely. So how do we balance this? We multiply them together, right? So we're going to get our numerator, which is the likelihood of our data. If we assume it came from a certain factory, we're also going to multiply it by the prior probability that it came from that particular factory. So the likelihood of getting 10 red if the bag came from A is 0.117. I'm multiplying it by the prior probability that just a random bag comes from factory A, which is 0.5. And I get 0.058. For B, we do what's the likelihood of 10 bags coming from B, 10 red if it came from factory B, and that was 0.176, highest likelihood, but we have to multiply it by the prior probability of getting 0.25. And then for factory C, 0.117 multiplied by 0.25. So these are the three different numbers I have for my numerators. So let me just pause there and just kind of check in and make sure this kind of makes sense, getting all of these numbers for each of these cases here. And so this is technically what our answer is, but what we need to do is we need to scale all of these answers so that when we add up the three probabilities, they add up to 1. Because right now, if I add up these three numbers, I'm going to get what? 0.11 or something? I'm not going to get 100%. So I need to just kind of scale everything up. And that's what, okay, I guess they add up to 0.13. That's what I'm going to put in the denominator. So the denominator is just the sum of these three numerator values, 0.1319, 0.132 basically, so that when I take the numerators and I divide by this, they're all going to kind of scale up by, by around, 7 times bigger or so. And then that way they will add up to 100%. That way they'll add up to 1. Okay, so this first value, I'm basically taking this numerator, 0.05857, and I'm going to divide by 0.1319, and I get 0.444. That's going to be the value after I scale it up, right? And this is found by saying, remember, we're doing Bayes' rule. What is the probability it belongs to class A if in my date, and if the observed data I have is 10 red out of 20 marbles? And we're going to say, okay, what is the probability of getting 10 red out of 20 marbles if class A has a probability of 0.6, and that's this value, that's the binomial probability, and we're going to multiply it by the prior probability of getting it from factory A, which was 1/2, 12 out of 24, divided by just what's the overall probability of getting 10 red regardless of factory, and that's equal to the sum of the numerators across all possible classes, and I get 0.44. I do the same thing for class B, and I get 0.33, and I do it for class C, and I get 0.222. And so these are the three different probabilities. So after opening the bag and getting 10 red and 10 blue, it's a 44% probability that it came from class A, 33% probability it came from class B, 22% probability it came from class C. So remember, in our test case was 50% red. So if we only used what we saw in our data, we would have said factory B is the most likely because, factory B is 50% red. Okay? But with the Bayes classifier, we also take into account kind of the prior probabilities, saying, well, before I even looked at the data, I know factory A produces the most amount of bags. So when we kind of combine those two, we get some kind of balance in between. Before we looked at the data, factory A was 50%. After we looked at the data, the probability came from factory A dropped down to 44%. Before we looked at the data, we would have said factory B has a probability of 25%. After we look at the data, the probability came from factory B goes up to 33%, whereas the probability it came from factory C, before we looked at the data, was 25%. After we looked at the data, it drops down to 22%. And so after all of these adjustments, after looking at the data, we say factory A is the most probable class at 44%. That's what we have here. There are some major assumptions going into kind of this example that we did. We said, one big assumption was I looked at the data and I said, all right, in my training data, for the 12 bags that came from factory A, what I observed was 60% red and 40% blue. And therefore, I'm assuming factory A produces 60% red marbles. That's a pretty strong assumption, right? We're assuming properties of the factory just based on, my sample of data, which could be wrong. And I'm also assuming, factory B is 50% red, and I'm assuming factory C is 40% red, just based on what I saw in my data, which, may or may not be right. I'm also assuming that because half of my bags, I had 24 bags that were labeled, and half of them came from factory A, I'm assuming factory A produces 50% of all kind of marble bags out there. And because only 1/4 of my training data came from factory B, I'm now assuming factory B is doing 1/4 of all marble production out there, right? And so these are major assumptions, which, to some degree they're reasonable, but it's also they might not be right. Okay, it could be. Let's say we are the owner of the marble company, and we know that I have 3 factories, and all 3 factories produce the same number of marbles. Okay? Well, in that case, I can incorporate that, and I would just say the probability it came from factory C is 1/3. Okay? But because I don't know that, and I'm basing it off of the data I have, I'm assuming factory C is only responsible for 25% of marble production. Okay? So how you put your numbers in depends on kind of the knowledge that you have and what assumptions you're willing to make. Let me give you your first view quiz answer, which is the letter C. C as in cat. C as in cat. C is your first view quiz answer. C. All right, let's say we do the same thing, but this time our test case, when we open it up, was not 10 red, but rather there were only 6 red marbles. Okay, so we open up, there's 20 marbles total, and only 6 of them are red. So my test case is only 30% red. Okay. And so now when we do our likelihood calculations, which bag is has the highest likelihood, or which factory has the highest likelihood? Okay. In this case, factory C has the highest likelihood, right? Because factory A we're assuming fills bags at 60% red. So could a factory that puts in 60% red produce a bag where it was only 30% red? And the answer is it could, but the likelihood of that happening is pretty low. Okay? What about factory B? Factory B we're assuming is 50% red. Could it produce a bag that's only 6 red out of 20? And it could, but it's less than 1%. And what about factory C? Factory C has a filling proportion of 40% red. Could that produce a bag that's only 6 red out of 20. And also it could, but its likelihood is pretty low. And actually, but it's the highest of all of these. And here I've multiplied each of these things by their prior probabilities as well. So I have the likelihood of getting, basically probability of getting 6 red out of 20 marbles if the filling proportion is 0.6 times the prior probability of 0.5. And I get 0.002. Here I get 0.009 and then 0.03. And so when you add all three of these up, your denominator, the marginal, is only 0.04. Right? And what this says is just when you look at this marginal of 0.04 versus this marginal of 0.131, basically this is saying it's much less likely that you're going to get a bag with only 6 red marbles than you are to get a bag with 10 red marbles. Okay, so the overall marginal probability of just getting this data of 10 red marbles or 6 red marbles, whatever it is, here the overall probability of getting 10 red marbles is 0.1319, and the overall probability of getting only 6 red marbles is lower at 0.04. But we don't really care. We just need, we want to use this to scale up the total answers, okay, which is going to be what's the probability of class A, probability of class B, and the probability of class C. And so if you take the numerator and divide by that denominator, after looking at the data, the probability that it came from class A is around 0.0567, so around 6%. Here it's around 0.216, so around 22%, and 0.727, so around 73%. So we got 73%, 22%, 5%, 6% there. Okay, so if your bag is only 30% red marbles, you got 20 marbles in there and only 6 of them are red, suddenly that makes factory C the most probable factory to produce this, right? Because factory C has the kind of the lowest red proportion. And factory A, despite factory A producing 50% of all marble bags out there, factory A is really unlikely to have been from factory A, because factory A has a filling proportion of 60%. So yeah, I mean it could produce a bag that's only 6 red out of 20 marbles, but it's pretty unlikely. So we have a low probability there. Okay. So the classification probabilities depend on what data we see, and that's how the Bayes classifier works. Okay, so I think this sums everything up, right? So in this test case, the likelihood of getting only 6 red out of 20 marbles is very low if it were to come from factory A, right? And getting 6 out of is not that unlikely if it came from factory C. So factory C is the most probable class assignment there. So we can, so that is kind of a very simple example of the Bayes classifier, and perhaps we want to use it for, something like where we have normal distribution. And so we'll look at the multivariate normal distribution. The multivariate normal, or the multivariate Gaussian distribution, we have, you can have d dimensions. A lot of times we can just illustrate this, the two-dimensional normal distribution, but you just have to kind of imagine in, higher dimensional hyperspace, the higher dimensional normal distributions. And this is the PDF. This is the PDF for a multivariate normal distribution. Let me pull up the PDF for the univariate normal distribution. There's actually a lot of similarities between the PDF of the multivariate normal and the univariate normal. So let's go to Wikipedia. Make this bigger. right, so here is the PDF. Oops. Oh gosh. PDF of the normal. And so what do we see? We have e to the negative 1/2, e to the negative 1/2. And here I have x minus mu transpose x minus mu. And that's kind of like x minus mu quantity squared. Okay, x minus mu quantity squared, right? So this is, with a univariate you have this, but with a multivariate you have these vectors. And so you have x minus mu transpose x minus mu. That's kind of like x minus mu squared. And but inside here we have divided by sigma. If you expand this out, we have sigma squared. And that is, we have the sigma, which is the covariance matrix, and we're going to multiply it by its inverse. So again, in matrices, there's no division, but you can multiply by an inverse, and that's similar to dividing. Okay, again, not quite, but there is a mathematical parallel there, right? And then similarly over here, we have 1 over root 2 pi, and I have 1 over 2 pi times d being kind of how many dimensions we have over 2. So if it was 1 dimension, it would be root 2 pi. But as we have higher dimensions, we have this thing. And then we have sigma, and here we have the determinant of the sigma matrix raised to the 1/2 power. So it's not exactly the square root of that, but there are some kind of parallel elements between the multivariate the PDF of the multivariate normal and the PDF of the univariate normal, which we are probably more familiar with. Okay. As far as the sigma variance covariance matrix goes, okay, you have this d by d square matrix, and the elements on the diagonal are going to be the variance of each component in your X matrix. So you have x1, so the diagonal element would be the variance of x1, the variance of x2, the variance of x3, and then the off diagonals will be like the covariance between x1 and x2, the covariance between x1 and x3, the covariance between x2 and x3. If your covariance is 0, then that means those variables are independent. Right? And you guys learned variance covariance for multidimensional data in, what is that, 100B? 100B, right? Yeah, so, okay, so you have that. Okay, so we're going to generate data, and here I'm going to generate from 3 classes, and these 3 classes will have equal amounts of data. So I'm going to have class A will generate 30 points, class B will generate 30 points, class C will generate 30 points. And I have, and so I can use this package MVT norm, which will calculate the density of the multivariate normal, and also can be used to generate random data from the multivariate normal. The mean of class A is going to be 2, 3. The mean of class B will be 0, 0, and the mean of class C will be 2, -2. So if I have so class A will have a mean up here. This is the mean of A. This is the mean of B. And 2, -2 is going to be the mean of class C. Oh God, you can't see it on the the little video here. And then you have a matrix 3, 0, 0, 3, 0, 0, 1. So for A, the sigma matrix for A is this. The sigma matrix for B is going to be, I think, the identity, and here the sigma matrix for C is this. Okay, so these are independent, and see, we're going to say we have 1, 2, 3, basically kind of independent matrices there. Here I've got kind of something that goes like that, and then here we have some covariance. It's going to look something like that. Okay, and I think if I use this to kind of plot basically what I have here, and this is what our diagram kind of looks like, and I guess my ellipses are a little bit more overlapping in the actual thing. So we can see this is centered at 3, 2, centered at 0, 0, centered at 2, -2. We have no covariance between x1 and x2 for class A, no covariance between x1 and x2 for class B, which is in blue, but we do have covariance between x1 and x2, which is in green here. Okay. Now, we generated this data, and so we know what the sigma matrices are for each of these things, and we also know what the mean should be for each of these components. But when we are doing the Bayes classifier, we have to estimate what is the mean of distribution A, what is the variance of distribution A. So how do we do that? We are basically, we look at our training data and we say, let's take the mean of all of the observations that are labeled class A. So that's all this says. It just says for everything in class A, add up the values in X and divide by how many observations you have. Okay, you're going to add up the vectors. And so when we do that, basically I'm going to take the observations in class A and I'm going to say, all right, what is the mean of the observations in class A? And I get 2.267 and 2.82. So remember that the true mean was 2, 3, and we get something kind of close, but not exactly that, right? The true mean of class B was 0, 0, and we're estimating based on the data that we have, and we get something not quite 0, 0. And then the true mean for class C was 2, -2, and again, we're getting an estimate that's a little bit off, because this is based on just 30 random data points for each of these classes. Similarly, for the variance, we can do, we take each of our observations and we subtract off basically the x bar, right? We say, okay, each value x minus, so I guess the definition of the variance would be our x's minus the true mean, right, squared. But in our case, we're going to do x minus x bar, x minus x bar transpose, and we're going to get this 2 by 2 matrix. And this would be kind of our MLE. However, if you use this, we're going to get biased values. And so we have to divide by n minus 1, right? And I don't know, you guys did a proof for why you do n minus 1 rather than n. The conceptual reason, which I think students do the proof, but then maybe they don't quite catch the conceptual reason. The conceptual reason is because what you really want is the distance from your random variables x and the true population mean, okay, which is somewhere. But you don't have the true population mean, so you're using your sample mean. Your sample mean is always going to be in the center of your sample. And so the distance from your random x values to the center of your own sample is always going to be a little bit smaller than the distances from your random sample to what the true population mean is. And so to kind of compensate for underestimating those distances, you divide by n minus 1. That's what it gets. So anyway, we're just going to ask, hey, what's the variance on what's the variance for the values labeled class A, what's the variance for the values labeled class B, variance for class C. And so remember the true variance was 3001, okay, and we have something. The true variances for class B was 1001, okay, and we don't, and then the true variance for class C, I think, was 3, 2.5, and 2.5 and 2. And so, class C, probably the variances are a little bit most off. And so, we can kind of plot those. And these are basically the estimated variance covariances and based on the estimated means. So these are the estimated kind of contour lines. These are the contour lines that correspond to kind of your 40% percentile and your 65, 80, 90, and 95 percentiles here. And if I plot that against the true values, so the true contour lines are shown in black, and our estimated contour lines are shown in orange, we can see, okay, the centers are a little bit off, and then the covariances are a little bit off. But these are just based on the random values that we see in our data, okay? And that's what we're going to use to try to estimate our class probabilities. So let's say I have a test case here at 0, 0. And I say, all right, is this class A, which is red? Is this class B in blue? Or is this class C in green? And we look at this and we say, okay, if it's at 0, 0, it should be class B, right? Now, technically, it could have come from class A, and if class A decided to generate a really weird point, okay? Could it also have come from class C if it did, class C generated a weird point? It could, but considering the ellipses here, it would be really, really, really unlikely for class C, the green class, to produce this point, okay? And it's pretty unlikely for red to produce this point, but not as unlikely for green. Whereas blue is going to be the most probable to create this class, okay? So we're going to use the same Bayes rule. And we're going to say, okay, what we want to know is what is the probability it's in a certain class, and we want to say, okay, what is the probability of getting our value 0, 0 if it came from red? What's the probability of getting 0, 0 if it came from blue? What's the probability of 0, 0 if it came from green? And we're going to get different likelihood numbers. We're going to multiply that by the prior probability, and in our case, our prior probabilities are going to be the same for all three classes because I said 1/3 of our data is red, 1/3 of our data is blue, 1/3 of our data is green. But again, you could imagine some other scenario where perhaps most of the data comes from red and only a few observations come from blue or green or something like that. But in our case, they're equally represented. And then the denominator is going to be the numerator summed across all possible classes. So I could use the PDF of the multivariate normal distribution, and I would have to do it like this, and I would do 1 divided by 2 times pi raised to the 2 dimensions, so d over 2 is 2 over 2, times the determinant of our variance raised to the 1/2, times e to the negative 1/2, times x, our new observation of 0, 0, minus x bar transpose, times the inverse of the variance, times x new minus x bar, and I get this number, 0.00087, okay? This is kind of a pain in the butt, all right? We could do it, but it's a little bit of a pain. Thankfully for us, there is the function dmv norm, density of the multivariate normal, and I can just say, hey, what is our new observation? 0, 0. What is our mean of A, which is, we calculated that, and what is the variance? And if you do that, it spits back the exact same number, 0.008795399, 0.00008795399. Okay, so we don't have to worry about using the normal PDF directly ourselves. We can just simplify our lives and just say, hey, use the density function from our package MVT norm. Okay, so we say density of the multivariate normal. I say, all right, what is the density of the multivariate normal for class B? And we get 0.165, much higher, class B being blue. And what is the density for the multivariate normal for class C, green class? Very, very small, 1.64 times 10 to the minus 5. So very low likelihood there, okay? The priors here are going to be 1/3 for all three classes. Class A, Class B, and Class C all have 1/3. So technically, I don't need to include them because they're all going to cancel out because they're all equal. But just for kind of completeness, I will include them. And so the numerator for each one is going to be the likelihood times the prior. And we'll do that for Class A, Class B, and Class C. And we add the numerators for all three classes. So my marginal probability will be the likelihood times the prior plus the likelihood times the prior plus the likelihood times the prior for the three different classes. That gives my marginal probability. And now the final kind of posterior probabilities is the likelihood times the prior divided by the marginal. So the likelihood was found using density of the multivariate normal. The prior was 1/3. The marginal was the sum of the numerators across the three different classes. And so when we do this, we say the probability that it came from class A is 0.005, about 1/2 of 1%. The probability came from class B is 0.995, basically, 99.5%. And the probability that it came from class C is, 10 to the minus 4, very, very small, like 1 in 10,000 probability. So as expected, when we look at this test case, we say 99.5% probability it came from class B, about 1/2 of 1%, and about a 1 in 10,000 probability that it came from class green. So that's how we get our probabilities there. Okay. Does that feel okay? Any questions? All right, let me give you your second view quiz answer. Second view quiz answer is the letter B. B as in bear. B as in bear is our second view quiz answer. Okay, what about this? If you just had to eyeball, which one's going to have the highest probability? Which one's going to have the lowest probability? Just eyeballing. What do you think? The test case is right here, 6,2. Any guesses? A, red, will have the highest probability. Lowest probability, what do you think? B, the blue one, okay? All right, and then something green will be somewhere in between. Okay, so we do these calculations. 6,2, I get the likelihood just by using the multivariate density. The priors are all 1/3. The marginal is the likelihood times the prior, summed up for all three classes, likelihood times prior, likelihood times prior, likelihood times prior. And then, so our final probabilities will just be the likelihood times the prior divided by the marginal, and we get around 80% A, 10 to the minus 9 for B, and then around a 20% probability for class C. So class A has the highest probability. Okay, all right, what about this one? Class A, class B, C, if you had to guess numbers. Okay, so here it's like, okay, we feel like it's pretty equally likely to be from red or green. And so if we put in a test case at 5,1, we can do this, calculate it. And so we do the likelihood for each of these things using the multivariate density. And we get around 39% for class A, basically 0 for class B, 10 to the minus 6, and then 61% for class C. So it's just a little bit more likely to be in the green probability than it is to be red, according to our calculations here. And then here I tried to pick one kind of right in the middle of all of these. And so if it was 2.53 and 0.37, then the probabilities for each of these things is very similar. 30.306, 0.358, 0.335. Okay, and that's based on our estimates, right, regarding the random data that we have. So if we had a different random data set, our contour lines would be a little bit different, and our probabilities would also probably be a little bit different. But based on the data that we have here, we're getting these numbers that are all very similar to each other. So that's how the Bayes classifier works. Okay, so again, to summarize, the posterior is the probability that we want to find, and that's going to be the probability that an observation belongs to a particular class. And that's found by doing the likelihood multiplied by the prior divided by the marginal. The likelihood is, what is the probability of getting those particular x values? What is the probability? So I know you guys are finishing up homework 4, but finishing up homework 3, I posted up homework 4. Okay, and homework 4, you're going to code up basically a Bayes classifier. And we'll use the IRIS data set again. And basically, you're going to say, okay, if it came from Setosa, right, based on the training data I have, I'm estimating Setosa's mean is this, Setosa's mean petal length is this, Setosa's mean petal width is this. And based on that, what is the probability that if it came from Setosa, I get a petal length of whatever, 5.1, and a petal width of, I'm making up numbers, 3.7, right? What is the probability of getting these particular x values? That's your likelihood. We multiply that by the prior. In your case, it's going to be the same. Prior is going to be the same for all 3 classes. And then you multiply, add them up, and divide to get your marginal. Okay? So that's your Bayes classifier. Actually, I think in the homework you're going to do the naive Bayes classifier, which is actually even easier. So that's the Bayes classifier. We can actually make our life a little bit easier with the naive Bayes classifier. The naive Bayes classifier, and then I would say the naive Bayes classifier is actually a little bit more popular than the general Bayes classifier. So the Bayes classifier is very flexible. Naive Bayes classifier puts additional restrictions on it by saying everything is assumed to have no covariance. But that actually simplifies our life a little bit easier. So for our Bayes classifier, we use the multivariate normal distribution. This is our multivariate normal distribution. The naive assumption in the naive Bayes classifier is that your x variables are independent. Your x variables are independent, which is probably a bad assumption, okay? But sometimes it's still okay, all right? Things still kind of work out. Like when you do linear regression, one of your assumptions is that you have constant variance. And in real life data, that idea of constant variance for the error term is rarely true. Okay. Does that mean linear regression is useless? No, it's still useful, right? It's just mathematically, there's this assumption going in play, but you can still get a useful linear regression model despite that assumption kind of being incorrect. All right. And similarly, this naive Bayes model can still make pretty good classifications and pretty good predictions despite this assumption that there's no covariance between between your x variables, okay? And that's because, and the reason why we might prefer the naive Bayes classifier is, we don't want to estimate the covariances between our x variables, okay? In order to estimate covariances between x variables, you need a lot of observations. And if you only have a couple observations and you try to estimate your covariance based on just a few observations, your covariance estimates could be really wrong, and that might end up messing up the performance of your predictions because your covariance estimates are just very wrong. And so instead you just say, hey, everything has a covariance of 0. And that's certainly wrong, but certainly it makes our things easier to calculate. And so when you say the covariances are all 0, your multivariate density function, your PDF of the multivariate normal, becomes a product of univariate PDFs, right? So when you think of your rules of probability, when you have independent events, you can just multiply those probabilities, right? you do probability of A times the probability of B, rather than doing probability. Normally, if they're not independent, you have to get the probability of A and B as the probability of A times the probability of B given A, right? But here you can just do probability of A times the probability of B. And so here we can say, rather than having covariance between all of these things, we can just say, let's figure out the univariate density for x1, the univariate density of x2, and we'll just multiply them together. So the entire PDF just becomes a product term of, and this is just the univariate PDF, the normal distribution PDF, and you do it for dimension 1, dimension 2, all d of your dimensions, and you just take the total product of these things. Okay, so we're going to use the same kind of training data. We have our three classes, A, B, and C. And this is the original data came like this, okay? And to do our estimates for the naive Bayes, we just need the mean of variable x1 for class A, and x1 for class B, x1 for class C. So I have x1 bar A, x1 bar B, x1 bar C, and then we have x2 bar A, x2 bar B, x2 bar C. So this is just column 1 and column 2 for the different classes A, B, and C. And then we're going to just get the variance or standard deviation one variable at a time. So standard deviation for x1 for class A, standard deviation for x1 for class B, standard deviation for variable 1 for class C. And similarly, we do it for the second column. Okay. So I don't have to do, I don't have variance covariance matrices. I just have one, a scalar standard deviation or scalar variance term. And so when you kind of plot the contour lines, when you assume everything's independent, basically when you plot the kind of the ellipses, the major and minor axes of the ellipses are parallel to your x1 axis and x2 axis. So the biggest difference is right here. For the green case, the covariance, when you have covariance, you kind of have these, ellipses that are coming in at an angle. And here we're saying, there's no covariance between x1 and x2. So you just say, hey, what's the variance of the green observations in the x1 direction? What's the variance of the green observations in the x2 direction? And they look like this. And so you get this kind of shape. So basically, the biggest flaw here is if you looked at the original data, we would say, hey, could the green class ever produce a value at 0, 0? And we would say, no, there's no way it could ever produce a value at 0, 0. Okay. Whereas over here, we're going to say, okay, it's not super likely, but it is possible for the green class to kind of produce a value at 0, 0. That's kind of your biggest flaw. But for these ones, the other ones, pretty similar there. Okay. So the most pronounced difference is again for the green dots, which when we generated our data came from there was high covariance between there, and here with the naive assumption in play, there is no covariance. And that's reflected here. Okay, so let's try this out. Let's say, what is the probability that it belongs to class A or class B or class C if we have a test case at 0, 0? Test case at 0, 0. And what's our probabilities here? Okay, so we do this the same kind of way. We say, hey, what we want is the posterior probability that it belongs to a certain class. And we're going to do this by calculating the likelihood of getting this data if it came from a given class, multiplied by the prior probability divided by the marginal. The key difference here is this likelihood. We will not use the multivariate normal density. We will use the univariate, just the regular old normal distribution, normal density, and use that and take a product of them. Okay. Prior, marginal, those are calculated in the same way. So rather than doing the multivariate density function, I just have the regular normal density, d norm. D norm is for a univariate normal distribution, and I'm going to say, okay, I have a new test case at 0, 0. So this is going to be what's the density of getting 0 if I have, mean for x, mean of class A, so x1 bar A, standard deviation of x variable 1 for class A. And then so I have the density there, and I multiply it by the density for the variable x2. Okay, so it's a product of two densities, and I get 0.00128. Same thing for class B, 0.16359, and then same thing for class C, I get 0.0094. So this is these are the densities here. So we have a product of normal densities. One thing, just so you don't make this mistake, when you do your homework, the next homework 4, and I ask you to do the naive Bayes classifier, make sure you use d-norm for the normal density, not p-norm. P-norm corresponds to the cumulative distribution function, right? Not the PDF. You want to use the PDF, which is d-norm. What did I say? P-norm? P-norm is the CDF. P-norm is the CDF. Don't use the CDF. Okay. Can a density go over 1? Yes, a density can go over 1. The probability cannot, the cumulative distribution function cannot go over 1, but a density can go over 1, right? Especially if you have a very small, like if you have a normal density, and if you have a very small standard deviation, okay, if your SD is like 0.01 or something, remember the entire thing has to integrate to 1, right? And so if the width on this thing is like really small, okay, in order for the thing to integrate to 1, the density definitely has to go above 1, okay? So densities can go over 1, but CDFs cannot. Okay, prior is 1/3 for everybody. Marginals, likelihood times prior for all 3 classes. We do that. And so we get our posterior probabilities. And so we have 0.007, 0.938 for class B, and 0.0539 for class C. So here we have, 94% probability that it's class B, and around a 5% probability for class C. And so, class B is still the most probable. And now I think if we look back a bunch of slides, with the regular Bayes classifier, not naive, it was like basically 10 to the minus 9 for class C, and now we're getting like a 5% probability for class C. Okay, so a little bit off, but that's how the naive Bayes classifier works. Okay, most of the time, the naive Bayes classifier will give you pretty decent estimates. Okay, we're going to finish early today. I've got one more application of the naive Bayes classifier, and this is where it is useful to have the naive assumption. Okay, and so you can use the naive Bayes classifier as a document classifier. So meaning you have text, right? You have documents, you have some kind of article or a story or something, and you want to classify it. This article is about politics. This article is about sports. This article is about finance or something like that, okay? We want to use the naive Bayes classifier because it doesn't require us to calculate covariances between words, because the way our matrix will be set up, our data is going to be, we're going to use what's called the bag of words model. And basically, we're going to get a count of how many times each word appears. So x1 might correspond to the word A, and x2 might correspond to the, I don't know, the next word in the alphabet, or in the next word in the dictionary, which would be what? Aardvark or something, and then, the next word. And you might have, I don't know how many words are there in the language, let's say 50,000 words. Technically, you would have 50,000 x variables, okay? And x1 is how many times did this word appear? X 7,000 would be how many times did the word house appear? Okay, X 20,000 would be, how many times did the word mathematics appear, or something like that, right? And the last one would be like, how many times or some of the last ones will be like, how many times did the word zebra appear, or whatever. And you have all of these different variables, okay? And the bag of words just says, that's all that matters, is how many times each word appears. And so the idea is, imagine having like in a cartoon, you have this document with words on it, and in the cartoon, maybe they shake the piece of paper and the words fall off the document, right? And so imagine, you shake the paper and then the words fall down, and now they are in, and you just collect them in a bag, okay? And so the order of the words is lost. In the bag of words model, the order of the words is lost, and it's just what words are in there, right? Because in a bag, there's no order of items in a bag, okay? Versus like a list, there's an order. In a bag, if I say, what is the third item in your backpack? That's a weird question, because when you reach into your backpack, what's the first item and what's the fifth item? There's no order, okay? So bag of words, you just, it's kind of like you shake the words off the page and they fall into a bag, and you just have the count of how many times each word, okay? Now, there are major limitations of a bag of words model. Because if you have, let's say this is the sentence, the document, it is bad, it is not good, okay? The bag of words would say it appears twice, is appears twice, bad appears once, not appears once, good appears once. That is what shows up in your bag of words model, okay? If you have this other document that says it is good, it is not bad, okay? It comes back with the exact same counts. It appears twice, is appears twice, bad appears once, not appears once, good appears once. So these two documents, they have opposite meanings, but they will get classified as the same exact thing, okay? And so, I don't know if it's still popular. Sentiment analysis. I don't know if you've heard of sentiment analysis. It's the idea of like, you scan Twitter, or you scan, I guess it's X now, or Amazon reviews or something like that. And you try to figure out, is the person saying something positive or are they saying something negative? What is the sentiment of this thing that they've written? And so my opinion is that if you try to do sentiment analysis with a bag of words model, it's going to just come out really bad, okay? Your performance for that is not going to be great. You're going to need a more powerful or more complicated thing, because, again, these two things have opposite sentiments, but they're going to get the same rating with a bag of words model, okay? They're going to get the exact same, because in the data, it's exactly the same. But anyway, just imagine you have this whole thing, and so you're going to have this kind of this lexicon, this dictionary of all the words. And in order for us to do document classification, we would need to have a lexicon of word probabilities for the different classifications. Okay, so here is a very, very, very simplified lexicon. And we're going to just say there are two, our documents will be either about fairy tales or will be about chess, the board game chess, okay? And we're going to have a very, very, very tiny vocabulary of just 8 words, okay? Again, in reality, the lexicon probably has 50,000 words, maybe 100,000 words, okay? Thousands and thousands of words. And you're going to have different probabilities for each of these words, right? And so, if it's about sports, words like team and player will have higher probabilities, okay? If it's about politics, words like senator and vote or whatever will have higher probabilities, whereas, goalie or ball will have lower probabilities, but sports will have higher probabilities for goalie and ball. Okay, and so here again, we're just limiting ourselves to this tiny vocabulary of 8 words, and we're going to say if it's about a fairy tale, you might have the word king and queen, or princess, right? And princess frequently shows up in fairy tales, so we'll say these are your kind of word probabilities, and you might have a knight in your fairy tale. Okay, the word rook is probably unlikely to appear in a fairy tale, so we'll give it a low probability for a fairy tale. Okay, we have good and evil that happens in fairy tales, but then talking about the board, okay, is probably unlikely to happen in a fairy tale. Okay, whereas with chess, king and queen probably likely to be spoken about in chess. But the word princess is unlikely to appear in a document about chess, right? Okay, rook will appear in chess. Okay, good, maybe like a good move. Sure, that could appear in chess. But talking about saying evil, evil in the chess game, probably not very likely. Okay, and a board is going to be very likely to appear in chess. So I just made up some numbers, but this kind of reflecting the idea that some of the words will be probable for both documents. Some will be much more probable for one document and much less probable for a different document class. Okay, and again, this is just a tiny version of what you might use in real life, which would have like 10,000, 50,000 words, 100,000 words or something. And you'll have a whole bunch of these probabilities that would, add up to like, 100%, okay? Most of them would be like on the order of like 10 to the minus 3, 10 to the minus 5 for these things. And here I have these, very high probabilities for each of these things. Okay, and so the lexicon, the way it's built up is you take a whole bunch of documents where the document class, and it scans all of those words and it tallies up. Okay, I see this word, I see this word, I see this word. And it kind of builds up these probabilities by kind of ingesting all of those documents. And that's how we do. It's also common practice to remove stop words like the, is, to, a, all of these common words that don't really give us information about what the document is about. Okay, so let's say this is a test case. And this is not good writing here, but we're going to say the evil queen sent the evil knight to capture the princess. Okay? All right, so do you think this is about chess or is this a fairy tale? Okay, and so, capturing the princess, that sounds more like it's about a fairy tale. And then, if it was just like the queen captures the knight, that could be chess. But the evil queen capturing the princess, it's got to be a fairy tale, right? But anyway, we count the relevant words that appear in our lexicon. We say queen appears once, princess appears once, knight appears once, evil appears twice. Okay, and so we take the probability of each of these things, right? So queen has a probability for fairy tale of 0.2. Princess has a probability of 0.25. Knight has a probability of 0.2. Evil has a probability of 0.11. And it appeared twice. So we square that and we get 0.000121. That's the probability of likelihood of this sequence of words. Whereas if it were about chess, okay, queen has a probability of 0.2, princess has a probability of 0.01, knight has a probability of 0.15, and evil has a probability of 0.01. And so the total probability or likelihood of this thing, if it were about chess, is much, much, much lower, 0.00000003. And then, you multiply by the likelihood, you divide by the marginal, and you can see, we'll see that this number, the likelihood that the probability is about a fairy tale is much higher than the probability that it's about chess. Okay, why is this the naive Bayes classifier? Well, we don't have any covariances. There's no covariances. covariance would be how likely, what is the covariance for this word to also appear in the document at the same time as this other word, right? So if you're talking about a king, there's probably a high covariance that a queen will also be mentioned in the same document, okay? I mean, higher probability, okay? And if you're talking about, I don't know, tennis, if you look at the word tennis, probably the word ball, racket, match, set, those are all going to be words that are going to have higher probabilities. And so there's going to be covariance between these words. The problem is what is the covariance between tennis and alligator? And is that a different covariance between the word tennis and house, or tennis and car, and tennis and elephant, And how do you estimate covariances between, 50,000 words, okay? If you think of 50,000 words, how many pairs are there? 50,000 choose 2, I don't know what that is. A really, really, really big number. Millions of covariance terms. And how are you going to even get accurate covariance estimates for these things? And so trying to get accurate covariance estimates is going to be a huge nightmare. So rather than trying to figure out what those covariance terms are, we're just going to assume there's no covariance. And that's probably it's not right, because we do know certain words do appear more frequently together, but rather than having to figure out, okay, what is the covariance between every single possible pair of words, we're just going to assume everything's much more is independent, and then our calculations can just be done by just taking products rather than figuring out, okay, what is the joint probability of queen and princess together? We can just multiply those probabilities together. And so this is how we would get the likelihoods. I didn't bother with the priors and the marginals, but you can understand, okay, this is one aspect of that, of the posterior probability, the likelihood part, and then the priors and the marginals are other parts and aspects and things like that, okay? Queen captures the knight. We have queen and knight are the only things, and so we have 0.2 and 0.2, and we have 0.04 for the likelihood of fairy tale. Queen captures the knight for chess. We multiply these two, 0.2, 0.15, so slightly lower probability for chess or whatever. And it's difficult to go off of just these things. But if you say, it's supposed to be queen captures the rook, okay, for fairy tale, very low probability. Queen captures the rook for chess, much more probable. So this is kind of how a naive Bayes document classifier could work, by just having a huge dictionary of possible words along with the probabilities associated with each of these things, and we just kind of take the product for the bag of words model. Okay, let me give you, I think I need to give you the last two. Okay, the last two answers are E as an elephant and A as an apple. E as an elephant, A as an apple are your last two VUEQuiz answers. And we'll just finish a little early. I hope that's okay to end class a little early today. And we'll see you on Wednesday.